Ax is equals to 0. A is matrix 2 0 minus 1, 4 0 minus 2, and x, that is the column matrix x1 x2 x3 is equals to 0, that is 0 matrix 0 into 0. Augmented matrix of this system can be transferred into the 2 0 minus 1 0, 4 0 minus 2 0. We want to find the solution of this system. For that we have to convert this augmented matrix into the row echelon form. For that, let a row operation, first row operation, that is a 1/2 R1, that is means divided first row into the by 2, and resultant matrix, that is 1 0 minus 1/2 0, 4 0 minus 2 and 0, and we converted this matrix into the row echelon form. For that, the below entry of this leading one must be 0, but here the below entry of leading one is 4. For reducing this entry to 0, doing this operation R12 minus 4 means multiply first row to minus 4 and add to the second row, and the resultant matrix is 1 0 minus 1/2 0 and 0 0 0 0. And the corresponding system from this augmented matrix can be written as x1 plus 0 x2 minus 1/2 x3 is equals to 0, and we have to find the value of x1. For using back substitution, we write x1 is equals to minus 0 x2 plus 1/2 x3, but here the equation is 1 and the unknowns that are 2, so we have to use the this is the case of infinitely many solution, and in this case we have to assign the variable x2 and x3 as the variable t1 and t2 respectively. For assigning this variable x2 and x3 as t1 and t2 respectively, the solution became x1 is equals to 1/2 t2, x2 is equals to t1, and x3 is equals to t2, and the final solution null space x is equals to x1 x2 x3 is equals to 1/2 t2 t1 t2, and let common t1 of this equation, and the t1, the coefficient matrix is 0 1 0 plus t2, and student note that coefficient of t2 is 1/2, and here 0, and here coefficient of t2 is 1, and this two column matrix 0 1 0 1/2 0 1, that is nothing but the basis for null space with respect to the Euclidean inner product space, and this null space A is equals to 0 1 0 comma 1/2 0 1, which is also the basis for W perp, means the basis for orthogonal complement of this row space. So here we seen that how the find the orthogonal complement, basis for the orthogonal complement of the subspace of corresponding span row space or column space. Now we discuss about the orthogonal projection. If u and v are two vectors in an inner product space V such that any non-zero vectors V, then orthogonal projection of u on V is given by this equation: projection of u on V is equals to inner product u comma v upon norm of v square into vector v, and the component of u orthogonal to the v is given by this equation. Orthogonal projection u on v perf is equals to u minus projection of u on v. Now we define orthogonal projection on subspace. In previous slide we defined the orthogonal projection on particular vector. In this slide we define the orthogonal projection on particular subspace. If v1 to vn is an orthonormal basis for the subspace W of an inner product space V, and W is any vector in V, then orthogonal projection of W, which is any vector on capital W, is given by this equation. Projection of W, that is the vector on this W, capital W, that is the subspace, is equals to inner product W comma V1 into V1 plus inner product W comma V2 into V2 plus up to so on, plus inner product W comma Vn into Vn. Student can be easily seen that how we define the orthogonal projection in the subspace W. Now if the vectors v1 to vn is orthogonal basis for subspace W, then how we define the orthogonal projection on V? If the vectors v1 to vn is an orthogonal, I again repeat, if v1 comma v2 up to vn is an orthogonal basis for subspace W, then the orthogonal projection W on subspace W is equals to inner product W comma V1 upon norm V1 square into V1 plus norm of W comma V2 upon V2 square, norm of V2 square into V2 plus up to so on, inner product W comma Vn upon norm of Vn square into Vn. Let us one example. Find the orthogonal projection of U, that is the 4 0 minus 1, along the vector V, that is the 3 1 minus 5 in R3 with respect to the Euclidean inner product. Also find the orthogonal complement, also find the component of U orthogonal to V. So here we want to find the orthogonal projection of U along the vector V, and also find the component of U orthogonal to V, vector V. So for that we use the equation. Orthogonal projection of U along the V is given by the equation. Projection of U on V is equals to inner product U comma V upon norm V square into V, and notice that here student can notice that here inner product is Euclidean inner product, that's why we write this inner product U comma V as the U dot V upon norm V square into V, and dot product of these two quantity 4 0 minus 1 dot 3 1 minus 5 and V square, norm of V square, that is the sum of square of the V element of V, that is the 9, that is the 3 square plus 1, that is the 1 square plus 25, that is the 5 square, and that is the only vector V 3 comma 1 comma minus 5, and the inner product dot product of these two 4 into 3, that is 12 plus 0 into 1, that is 0 plus 1 into 5, that is the 12 plus 5, that is the 17 upon 25 plus 1 plus 9, that is the 35 into 3, 1, minus 5. The resultant value is 51 by 35, 17 by 35, minus 17 by 35. So this is the value of projection of u on the vector v. Now we want to find the component of u orthogonal to the vector v is given by the equation projection of u on v perf is equals to u minus projection of u on v. We already find this value projection of u on v. So write this is equals to 4, 0, minus 1 minus of this projection of u comma v, which is the value of 51 by 35, 17 by 35, 17 by 35, and that is put this value in this equation and simplify this to value. We get 89 by 35, minus 17 by 35, 10 by 7. So here we seen that how find the orthogonal projection of any vector along to the another vector, and component of that vector along orthogonal to that vector, and student can easily verify that this you can also find orthogonal projection on the subspace. Just write w instead of w v and v per. Here you can use w and w per for the finding the orthogonal complement of orthogonal projection of subspace on the subspace. Now we discuss about the least square approximation, means least square solution. In my first lecture I discussed about the system is consist if the solution is given, and the system is inconsist if the solution is not possible of the system x is equals to b. But in many situations the system x is equals to b requires the solution, and this solution we find the solution x, which is the approximate value of the system x is equals to b, and that is the solution of system x is equals to b, and that solution is called least square solution. Now we define two theorem. A vector is a least square solution to x is equals to b, that is the non-homogeneous equation, if and only if x is the solution to the normal equation A transpose A x is equals to A transpose into b. Means if we want to find the solution least square solution x, which is the approximate value of x is equals to b, we want to find A transpose A x is equals to A transpose b value. If we find this value, we get the value of x, solution of this system. Okay, so let us another theorem. If x is the least square solution of this system x is equals to b, and the w is the column space of A, then projection of b on that subspace w is equals to ax which are the column space of that vector. Let us one example. Find the least square solution of the linear system x is equals to b given by x1 plus x2 is equals to 7, minus x1 plus x2 is equals to 0, minus x1 plus 2x2 is equals to minus 7, and find the orthogonal projection of b on the column space of A. Here I again repeat that least square solution is the particular solution for that the system is inconsistent. A student is verify easily this system is inconsistent, but we have to get the solution of this system. For that we using this theorem, least square solution, we find the solution of this least square solution. For that, converted this equation into the matrix form, 1 1 minus 1 1 minus 1 2, that is the matrix coefficient matrix of this. x1 is 1, x2 is 1, minus x1, x2 minus x1 and x2, that is the nothing but this matrix, and that is the system column vector of the system x, that is the x1 and x2, because here only two column, for that we choose only two variable x1 and x2, is equals to 7 0 minus 7, that are the value of this the coefficient matrix B, 7 0 minus 7. So after the writing in the matrix form, here notice that this is the coefficient matrix A, 1 1 minus 1 1 minus 1 2, that is the coefficient matrix B, 7 0 minus 7. Now we want to find the A transpose A. The student easily find the A transpose, that is the interchange of row and column of this matrix A, that is the 1 minus 1 1, then here interchanging column into the row, 1 minus 1 minus 1, and 1 1 2, interchange that column into the row, 1 1 2, and A, write A as it is, 1 1 minus 1 1 minus 1 2 is equals to, if we multiply these two matrix, the resultant matrix is given in the form 3 minus 2 minus 2 and 6. Now we doing solution. For that we also require the A transpose B is equals to 1 minus 1